Yay!
Yay! One more interesting thing you might find in kinematics is a two-dimensional collision. Now, sometimes what we mean by collisions is that we'll conserve momentum, but that's for a later unit. But maybe what we want to know is, will two objects collide or maybe intercept? So maybe I've got this object V, right? And V, I think I put V over here at, let's see, oh yeah, -4, 3. Those are its coordinates. And it's traveling at 2 in the X and -1 in the Y, right? 2I minus J. And then I'm sitting down here, maybe I'm the red object. I'm sitting down here at X equal 1, Y equals -4. That's my position. And I want to intercept it, right? I want to fire some projectile that'll intercept the thing. So what I want to know is, what is that vector for the projectile? How am I going to intercept V if I'm sitting down there at S? All right. So what this really is a two-dimensional collision. I want to find out at some time where am I going to collide with this thing? Okay, so we're free to choose because I can choose any time I want, really, as long as maybe if that's, an asteroid headed for the planet or something. I mean, there's some sort of deadline beyond which, I want to make sure I intercept the thing. But anywhere along that path, I could choose to intercept it. So I'm going to choose I'm going to choose 4 seconds. So how am I going to intercept this thing in 4 seconds? What I'm going to use is this up here. I'm going to use our definition of V. But notice we're in 2D now. These are vectors. So before we've always done motion in one line, just X and Y. So let's use V is now, the definition is that it's delta R over delta T, where R is the vector, X and Y, right? So let's write this down in a little bit better form. This means that my delta R is V delta T, right? So that means my R final minus R initial is V delta T. Or here's the useful way that we'll write it. R final, my final position is just my initial position plus V delta T. All right, I'm sort of just updating my position from where I was, R initial, to where I'm going to be, because every second I'm moving along that velocity vector. After 1 second I'm here, right? And after the next second, moving along that vector, now I'm here, and then I'm here, and then I'm here, and so on. Okay, so what does it mean for one thing to intercept another? What it means is that they're both in the same place. So here's our condition. This is what we're going to do. What we're going to say is that R final for the blue object is going to be the same as the R final for the red object, right? When one intercepts the other, they're both at the same position. So I'm going to set those things equal to each other. So here's what I'm going to do. What is my R initial for the blue object? It is -4 and 3. And then my V delta T, my V is 2 minus 1. And then I've chosen 4 seconds. I'm going to intercept this thing after 4 seconds. All right, that's going to be its final position, right? Maybe it's right there or whatever. That's got to be the final position for the red thing then too, right? The thing that I launch. So this is going to be equal to, what is the initial position for the red thing? I said it was 1 and -4 plus. Now here's what I don't know. I don't know the velocity vector, right? I need to know what the vector is along which I launch this thing in order that I intercept the blue thing. All right, so I don't know what it is, so I'm just going to call it W. That's what I'm after, times the same amount of time, 4 seconds. Right, there I go. Okay, so what I'm going to do, this is just a vector equation. No problem, we can manipulate vectors, so I'm just going to manipulate these vectors as their own little objects, and I'm going to solve for W. All right, so we know how to do this. This is going to be -4 and 3 plus, I just multiply a vector times a scalar there. I'm just going to multiply each component times the thing. So that's just going to be 8 and -4. This is equal to 1 and -4 plus 4W. Okay, neat. All right, so on the left-hand side, I'm just going to add those vectors together, just like it says. So let's bring it over here. So on the left-hand side, I've got, what, -4 plus 8. That's going to be 4. 3 plus a -4, -1. Is going to be equal to, apparently that's where these things are going to collide. This is 1 -4 plus 4W. Okay, now I just subtract that vector from the right-hand side to the left-hand side. So what do I get? 4 minus 1, that's going to be 3. 1 minus a -4, looks like that's also going to be 3, right? Equals 4W. So I'm just doing vector algebra. So now I divide both sides by 4, so that means I divide both components by 4. So my velocity vector is just going to be, what, 3/4 and 3/4, right? So that's 0.75 meters per second. There we go. So if I launch something, there's my vector. If I launch something at 0.75 and 0.75, 0.75 in the x, 0.75 in the y, then after 4 seconds, I will intercept that blue thing. Bang. That's what this is. That's what this is really telling me. Okay, very cool. This also kind of gives you a way to determine. Suppose, let's do something just a tiny bit different. Suppose that we know ahead of time. Maybe I've got 2 objects traveling along these tracks. Maybe I have this object traveling along the blue track and then an object traveling along the red track. And maybe I want to know, do these things collide? So now forget that we just did that problem. Now let's say that we're given that. We're given the blue position of velocity and the red position of velocity. Do they collide? So what's the test for collision? The test for collision is at some time, are they at the same place, right? So let's write that down again. But now maybe you don't know what the time is, right? You just want to know at some time, are they going to collide? So what you would do, the test for collision is just going to be making sure that those final positions are the same for each. So you would start out with -4 and 3 plus 2 and -1 times delta t. And that final position has to be equal to this final position. I start out at 1 -4 plus 0.75, 0.75. Uh-oh, ran out of room. That's times my delta t also. Okay, so those are the 2 final positions. I'm just setting them equal because I want to know, is that true? Are they going to be at the same time? Are they going to be at the same place? That's what it means to collide. So this is something that I would want to check. And so what you do is you solve for delta t. There better be some delta t that satisfies this equation. And when you do this, if you do the vector algebra, what you should find is that delta t is 4 seconds. That's not surprising. We sort of already found that, right? But this is the way that you can test for collision. So if you put those numbers back in, and then you solve for delta t, when will they be at the same place? What you'll find is that it'll be 4 seconds. Now you can cook up another example where these things do not collide, right? You just alter the trajectory of one of the particles, make it a different v. And what you'll find is maybe they don't collide at all. And what that means is that when you try to solve this for delta t, you're not going to get a solution. Right? You're not going to find a delta t that satisfies the equations. Okay, neat. So you can do two-dimensional equations with these simple formulas too.